Okay, and a good morning to everyone. The few that are here. We have the march in Sacramento this morning. So, well, we're doubling our number quickly here. Okay, so we've gone to 100% more. Reminder, please be here at 10:01, not 10:03. So, but I'm not very pleased to see some of you here. It makes me feel less lonely. We've got a large number who've gone up to Sacramento today. And that's because of the march they're doing up there, and so I knew a number of people would be absent, and they are. A number is anything 0 or higher, right? Okay. We are going to start with Q&A, questions and answers. Today the intent is to cover 6-1 on decimals. And I wanted to do a little bit of an update, some things that I've done. Before we start that was Fleetwood Mac and Jennifer. Secondhand news. I've been giving you secondhand news the last few minutes. Jennifer tells me she heard in the news already this morning that people were going to be in Sacramento. I think we have 600 from MJC up there. So that's a large group, and if think in terms of 100 colleges, if 600 went from each, that'd be 60,000 people in Sacramento marching around the Capitol. That's quite a large number.
Walking around?
Well, I think in some way showing their presence. So, no, 600 went up from here. Yeah. And so, but for those of you who are here, we will feed you numbers. Better than food.
No pie?
Oh, pie, yes. 3.14, 159, anytime you want. Give you pie anytime you want. Jennifer, I'm going to take a moment here as soon as I get this back out to where I want it. Okay, just to scroll down. This is our, whoa, I didn't want that. Let's see if I can get this where I need it. Okay, let's go to the document cam now. This is the video-based Math 20 homepage, which will eventually be a video-based page. And I'm trying to update things on there. So before I go much further, question, Natalie.
What does video-based mean?
Okay, video-based. It refers to a distance learning concept, and so the intent is to provide 60 hours of lecture that we've done. Everything that we have done this semester is going to go on to streaming video. And so there'll be 60 hours. And the idea is you could go back at any time and watch all the lectures. Then I will also make video clips, which means I go through and rewatch all the lectures and try to make somewhere between 300 and 400 video clips based on content. So if we had something about substituting, evaluating an expression for certain values of the variable, then I would have a clip where we'd spent maybe 2 or 3 minutes discussing that. So the idea that you could go 24/7, 24 hours a day, 7 days a week, no passwords necessary, and you could go ahead and you could watch material on questions that you had. And, pardon? Well, my intent is when this semester gets done that I'll have that for you. My hope was that I could do that as I was doing this semester, and I cannot.
But it's always available in the library, right?
The tapes from the lectures are available. So we have all the lectures on VHS tapes over in the library, but this would be streaming video, and then my intent is also to have that on DVDs. So you could buy, like right now we do in Math 70, Math 90, 134, Math 10. There's a DVD set that you can buy with all the lectures. All the board presentations will be, they have been photographed. I put those in JPEG files in reverse so that you have a whiteboard in essence, so you don't use a lot of ink as you print them. But all that will be available. And then that is available for anybody to watch 24/7. So what I've done so far as I come back, as we go back to the page now, What I've tried to do as we scroll down here, and this is just to bring you up to date with things that have just happened in the last hour. This is the spring 2009 schedule, and it looks different than it has. I thought it made more sense to come down now, and as we look at the chapters, they are by sections. So this is what we did each week, and this is where we are starting with week number 10. And notice it's 6-1, 6-2, 6-3, and 6-4. And then, as you scroll down, this is new. As we scroll over, here's exam 3. And as I click, each one of those has been done now. Here's exam 3. And it tells you what sections will be covered in exam 3. So it'll be 5-4 all the way through 5-8. It'll include chapter 6, 7, and 8-1, 8-2, and 8-3. So I don't know if that's depressing or not, but you have that. And then as I come down there a little bit further, let me bring it back to the left side. Okay, and then as we look at that, it gives how many questions will be on the test. So it tells you the number of questions, how many from each chapter, documentation, the exam, notes, calculator use, etc. Brings you back to the home page as we come off there. And the question, of course, is when that exam is, and it indicates to you that it'll be the week of April 6th, and that will be, at the end of the week, will be a Thursday. So that's there, and also it tells you where we're going finally up through the final review. And there's a similar statement about the final that's posted now. So as I bring this down just a little bit further, and I haven't put a date on there yet for the final. I will put that up, but this is, again, what chapters will be covered, and chapters 1 through 9. There will be 40 questions on this test. And again, about 4 from each chapter, and the usual statement about documentation and so on. So just, it's been updated, much more information there than had been in the past. And part of my hope maybe is to try starting to put the photographs up. I can do that from the board presentations, and so that all I will have to do is the lectures, which is about, just doing that is about 75 hours of work after the semester ends. And then it'll be about another 100 hours to put the video clips together. And so a lot of time yet to be done, but that's the hope. So I just wanted to update where we are. So if we look in terms of what we're supposed to be doing this week, again a reminder that we are, let me scroll this back up just so we can focus on this week. And this is the 10th week. And remember, there's only 15 in the semester. And so as we look at this, that's 6-1, 6-2, and 6-3. And the questions that still seem to exist are on 5-7. And just a comment for you about 5-7. I went ahead on the request that I received an email this morning, and I've opened that up through the end of the week. 5-7. So 5-7's up there. Now, let me caution you about one thing. It's the old 20-80 rule. Don't put all your effort just into 5-7 at the exclusion of everything else. So you need to make sure that you are paying sufficient attention to 6-1 as we talk about it and the previous material, because I'm not going to have 80% of the test in 5-7. There'll be a problem, maybe 2 problems from that section. It's nice that you're trying to get it done, and yes, it's demanding, but again, don't overstudy that section. As we go into 6-1, just to put in perspective what we are going to be doing in Chapter 6, it is, again, as so many times, it's Math 10 revisited. And there's not anything that's really in 6-1 that you shouldn't be able to do last week. The title for where we're headed, before I answer questions about 5-7, as we look at the document cam, it's decimals and rational numbers. Decimal notation. Okay, and the kinds of things that are done here, we've done before, and if you were to read through every single explanation here, I think you would find the comfort level tremendously easy for you compared to where we've been. There isn't a thing that's required in the problems here that you haven't seen before, with possible one exception, and that's which number is smaller than another. And so as I look at a problem, and this is where we talk about using inequality, write a true statement, and this is in an objective here, 413. Let me just summarize what's stated here, because I'm a little bit concerned once we start talking about 5-7, we'll never come out of it, a little bit like an abyss. But I'm looking at less than, greater than, and here's where you tend to get trapped a little bit here. If I look at 5.13, okay, we'd say 5 and 1300ths, correct? So the and is a decimal point. That's exactly what this author does, 5 and 1300ths. And if I compare that, so look at two numbers, compare. 5.2. And I ask, which is smaller? When you want to make comparisons like this, I would encourage you to go ahead and make sure they have the same number of digits after the decimal point. Now I think it's fairly clear that 5.13 is smaller than 5.2 because it was 5.20. If you left it as 5.2, I think that can get confusing. So we say that 5.13 is to the left of 5.13 is to the left of 5.20. Well, when we say left of, we mean less than. So this is read as less than. We have to be a little bit cautious if I'm comparing these two numbers. I'll put an and between these, and this is a nice contrast. As long as both decimals were positive, I think it made a lot of sense just to look at it usual, which is larger, which is smaller. But now you have to think of the number line. Which one is to the furthest away from 0? And in this case, negative 5.20 is to the left of negative 5.13. That's where you have to be careful. Now, as you think about where they're located on the number line, I hope it makes more sense to you to go ahead and do it as a distance. How far away are you? Here, when you think of distance from 0, it makes sense because 5.13 is closer to 0 than 5.20. If I go ahead and draw the number line for this first one, this is the only thing in this section that I believe is maybe a problem for you. This is 5.1, and let's see what I can do here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll make this go out a little bit longer. Okay, so this was, let's call this 5.0 right here. This is 5.2, 5.4, 5.6, 5.8, 6.0. Now, if I do that in terms of a grid, what your text then talks about doing is zooming in between 5.1, so 5.1 is here, And do the same kind of thing now going between 5.1 and 5.2. So what I'm going to try to do is line these up the same way I did before. Let's see if I can do that carefully. And we'll get an idea of what's going on here in a moment. Okay, so this is now going to be, let's say this is 5.10, 5.12, 5.14. Helps if I make that look like a 1-4. 5.16, 5.18, and finally 5.20. Now, if I play this game, I have 5.13 is here. And remember, 0's out here somewhere to the left. And here's 5.20. Now, which one is farther away from 0? Well, clearly, I hope this is, correct? Even though we sometimes think of it as just 5.2, it's supposed to help you to zoom in, and that's the phrase that's used in the text. The difference between 5.1 and 5.2, break it into 10 pieces. And way the heck out here is 0. So you're much further away at 5.2 than you are 5.13. The number here is to left of this. Now, if you would just flip this over here, I mean literally flip it in terms of what you see, and then make each of these negatives, then this flipped over there would have the negative 5.2 further away than the negative 5.13, and that's what this is saying. So negative 5.2 is to the left of negative 5.13, but 5.13 is to the left of 5.20. That's the only place where I think there is potential difficulty. The rest of section 6.1 is simply trying to get you to say that if I have 5.13, so I just start with 5.13 and I write it using words or verbal notation, word form. You say 5 and then you write the number that's after the decimal point, which is 13, and then you write the place value of the last digit, which is exactly what we did in Math 10. And we said this is going to be hundredths. So again, the whole part you write to the left of the end. So 5 and. Then you write whatever's to the right of the decimal as a number, and then you look at the place value of the last digit, hundredths. The other part here is to remember that that is the same as 5 plus 13 over 100. Because if you have 13 hundredths, that is the same as saying 5 plus, and that is 513 over 100. And so I can write a common fraction for this decimal. And we've done that before. We refer to these decimals as rational numbers because I can take any decimal that's terminating or repeating. So just to come over here, any terminating or repeating decimal can be written as a common fraction. Now, of course, a common fraction can also be written or called a ratio. A common fraction also known as, AKA, rational number. Now, I keep reminding myself as I write something like this, and I used to call this the newspaper column form until I started using a BlackBerry. And now, this is the way, of course, you try to have everything come down, scroll down on your cell phone so that you don't have to be scrolling back and forth. So you try to have one column on the cell phone. So I feel like I'm doing cell phone text messaging at this point, doing this kind of thing. The idea is that a decimal that either terminates or repeats. So terminating would be what? Like 0.25? A repeating would be like 0.3333, etc. Those can be written as common fractions. So I titled this section in the Math 10 book decimal fractions. Not just decimals, I called them decimal fractions because in essence you can rewrite them as a common fraction. Now, teasing Natalie about feeding you numbers and going to pi, just a reminder that pi doesn't repeat, does not end, so it doesn't terminate, does not repeat, and so it is not rational. It is irrational. What we used in these last few sections, we used pi as 22 over 7 as an approximation. We call that a rational approximation. So these are the things that are done in 6.1. And except for comparing two decimals and asking which one's larger, that's about all there is in 6.1. And it's a nice review of something I hope that is indeed a review. We even round off, if you'll remember. We round off decimals, and that's something that's talked about here. The process I just did, the root word names, just if you want to review that in your book, it's on 412. Okay, and it's exactly what I just talked about. Hopefully that'll be a review for you. This is on 412, and this is the verbal notation. And I love the fact that, and this is certainly comfort for me in terms of what I like, it's the blue material on 412, but writing the word and for the decimal point, it's just like reading my own writing nearly, presented in a different style, but it's exactly the things I've been doing in Math 10 forever, and it's nice to find a Math 20 book that is so consistent with what we were doing. The only difference here, he calls it a word name, and I call it verbal notation. And of course, what's fun is to go backwards. So remember the problems where we started with something like this. We said 489 10 millionths. Well, you had to go all the way out in place value until you got to what? The 10 millionths position that I'm pointing to with the red pen. Then you wrote your 489, so it ended there and then filled in the zeros. That's the only disappointment I have in the text in 6.1, that you aren't being pushed to go backwards a little bit more. To round off the usual procedure on 4.15, this is one I think you're probably comfortable with. To round off a number to a given place value. So let me slide that over just a little bit. To a given place value, you look at the digit to the right of that place value. And if it's 5 or more, round up. If the digit is not 5 or more, round down. So when I look at something like the 5.13 that I have here on the board, if I were going to round off to the nearest tenth, so 5.13 to the nearest tenth, T-E-N-T-H, I go to the tenths position. That was the place value. I look to the digit to the right. It's under 5, so I round down 5.1. And you don't put anything after the 1. Well, if I put a 0 there, then I'd have a hundredths position. And that, I wanted to go to tenths. So if I put a 0 there, it would argue that I might have had 5.103.
Right.
So we only have the tenths digit shown if I round off to the tenths. Again, that's not new to you and very consistent with what's done in the book. So I think 6-1 is a cakewalk. But not always correct in that assessment. That has been set up for you on the computer, and the problems are there that you're going to do, and I don't anticipate any difficulties there. The notation I thought was rather interesting. If we look at the place value chart, this is on page 410. There's something I wanted to bring to your attention because I thought it would be the kind of thing I'd do, which you had grown about. But here's my place values, the ones, the tens, hundreds to the left. And then the tenths, hundredth, it's where you bite your tongue as you have the TH at the end. And I sort of like what's done there. Okay, and here's a question, a discussion question that goes here as we come off there for just a moment, Jennifer. Here was a discussion question that I sort of liked. Why is there no once place? I like that question. Why is there no once place? Yeah, because it sounds funny. That's true. But as we come back and look at that, we talk about the ones place, but when you divide to the right, coming off there for just a moment, and I come up to here, and I've divided by 10 each time as I go to the right. And that's something I would have liked to have seen. That as you're going this direction to the right, you're dividing by 10. Hence, this becomes 1 over 10, which we call tenths. And we never get something where you'd have a once. I thought that was a good question. Another comment here, and I like, again, because it is, what do we mean by a rational number? Okay, and it's something I want to share with you in just a moment here, because the idea is you can express it as A over B. Now that's, again, page 410. And just a comment here in passing, and then I'll go to some questions. A rational number, and there's a statement that should be made here that amplifies a little bit what the author's saying. A rational number is of the form A over B. B not equal to 0. A and B are integers. So that means it could be positive or negative. And the argument here is that it's reduced. That A over B is reduced. That A and B have no common factors other than 1. And A over B is reduced. Now, if I make that demand, that A and B is reduced, and that every common fraction can then be written as a rational number where A and B have nothing in common. That becomes a rather important statement for another irrational that we talk about. I just want to throw this in the mix briefly to relate to something we did in the past. Remember when we had the unit square, 1 by 1? We did the diagonal. With the diagonal, we went ahead and used the Pythagorean theorem, and we said the diagonal was the square root of 2. How do you know that the square root of 2 cannot be written as a common fraction, A over B, where A and B are in lowest terms? So that's the question. How could we establish that this cannot be written this way? Okay, and I'm going to outline that a bit as we go to the right other side there briefly. So we're going to switch cameras here. And this is something that I typically show in an algebra class. And since we have a day where I'd like to go ahead and, in a first section of 6, add a little more content, let me walk off camera there. I'm going to go over here to the side. Most of you are familiar with the form of reasoning that's called this. Ah, come on, Curl, get your act together. Reductio ad absurdum. That's Latin, reduced to an absurdity. Now, it's based on a form of logic that says you have P or Q, one or the other. Not P, therefore not Q. Therefore Q, I'm sorry. You have P or Q, not P, therefore Q. So this is referred to as predicate logic. And the idea is we have simply a statement that's, you've heard it before, eat your dinner or no dessert. Okay? At least that's the way my mom put it. You clean up your plate or no dessert. So, if you didn't clean up your plate, guess what? No dessert. We do it in other ways, but we set up this kind of exclusive one or the other. Well, we could say the square root of 2 is rational or not rational. So it's one of these two. So if I try assuming this is true and show that that this isn't, then it must be this. So again, this is sometimes referred to as indirect proof. You are guilty or innocent. I'll assume you're innocent and show that that gets us to nonsense. It reduced it to an absurdity. Okay? Now, something bothers me, absurdum. That O should be an M or an U. I'm going to have to check that, but that bothers me. Reductio ad absurdum. One of the may have a missing letter there. So it's P or Q, not P, therefore Q. So here's what's done. You assume that I can write this as A over B. I'm just going to outline this briefly because it's a neat little argument. Square both sides. So that means 2 is A squared over B squared. And then I can cross multiply. So that says A squared is equal to 2B squared. Okay? So again, I assume that I can write the square root of 2 as A over B. Then I cross multiply and square both sides, or I squared both sides and then cross multiplied. So 2, squaring this gives you 2. Squaring this is A over B times A over B, A squared over B squared. And this is a neat result here because it says what? That A squared is even. Well, 2 times something is going to have to be even, right? Because I can divide it by 2. Okay, so that says A is even. Well, it just means it can be divided by 2 with no remainder. It's an even number. A is an even number. So that says that I can write A as something times 2. Sometimes we just use a letter K. So let's look at what we have. 2K squared equals 2B squared. And solve for B squared. And look what you get now. B squared must be what? Even. So that says B is even. That's absurd. If A is even and B is even, then I could have reduced this, correct? But my assumption was what? That A and B were reduced. So one more time, I started, let's assume that I can do the square root of 2 as a over b, and it's reduced. Well, when I do that, I find that a must be even, but then that tells me b must be even, and that's absurd. Therefore, this can't be, and I'm forced into what? That the square root of 2 is irrational. And that is the classic proof that is done in mathematics based on this idea that's in section 6.1 that a and b, when you write them as a ratio, are integers, and I'm saying reduced. Okay? And that was what we had in camera 1 as we go back there to that right side briefly, that a over b is reduced. Rational number. And I'm not going to ever bring this up in a test. But I want you to understand what proof is in mathematics. And this would be a mathematical proof that typically I do in a Math 70 once, and then I find that hardly anybody else does in Math 70. And I bring it up at times in a Math 90 or a calculus class as, what does it mean for a number to be irrational and what's involved? Okay? Natalie, question? 2, 4, 6, 8, 10, even numbers. So to say that A is even, it's like a 2, 4, 6, and 8, and 10. And to say that B is even, it's like a 2, 4, 6, 8, or 10. If both numbers are even, can't I reduce them? But I assumed what? That it was already reduced. Hence the absurdity. I assumed innocence and found out, well, if you were innocent, you couldn't have been there. I have a picture of you. Therefore, guilty. Court of law. Okay, I'm going to leave that and come back. And that is what, let's come back to the document cam for a moment, is exactly what's done here with what we call a rational number. Okay, and again, note the denominator can't be 0. Now, just another comment coming off there for a moment that's worth saying, because I've talked to you about this before, and it's worth putting some pieces back together now. And it has to do with how many fractions do I have? How many fractions could I have? A bunch. Okay, can you state it better than a bunch? What would be another word for a bunch? Infinitum, infinity, an infinite number, correct? Agreed? Okay, and before I do that, I want to clean something up here because I had a sneaking suspicion I had done it badly, and I did. Let's go back to the document cam. It is a U, absurdum. Good old Google. And I have a spelling error here that bothered me. Okay, so this should be UM, absurdum. My apologies as we go to the board. I didn't expect a croak from there, but absurdum. Let's slide over. Yeah, but it's just spelled correctly now. And go back to the document cam. And there's your reducto ad absurdum. And since we're doing a little bit of Latin this morning with Greek numbers, reduce, the idea. They did a reductio instead of reductio, reduction, where I had reducto. So reductio. Yeah. Okay, let's come back to what we have here. And Latin, if I come up to the source of all wisdom in the world, Wikipedia. I'm being a little bit cynical there. But the idea that it's Latin for, there we go, and this is from Wikipedia, reduction to the absurd. Okay, and proof by contradiction is another way of saying that's a nice statement for it. So proof by contradiction or reduction to the absurd. And again, it's based on this idea that we have in the process set up what is called an exclusive use of or. Okay? Now you have to be careful here. the word or that we use in English commonly speaking, if I say to Sarah, I'm taking you out to dinner or to a show, and as long as I do one of them, that's okay. And if I do both, she's not going to get upset. Okay, so if I say dinner or a show and we end up going to the show and a dinner, she doesn't say you lied. The use of the word or allows both. Now, if you are in the exclusive use, this or this, when you try doing both, you have a contradiction. Okay? So you can't be guilty and innocent simultaneously. And so in this sense, we set up this exclusive use of or. You try to establish that the P is not true, therefore Q follows. And again, that's referred to as predicate logic, and you get that in a philosophy course. We call this a syllogism. Means not. The squiggle in front of the P means not P. Okay, now that's two of them together would be approximately equal. Okay, so again, coming back to the document count, and that's where we have reductio ad absurdum. Okay, so that was just something extra for the day. The homework on these problems, pretty straightforward. So the question, what would I have you doing? And so let me come back from where we were there to week 10. Just this is because it's been requested at times. So I'm going to go back to week 10. I'll be there in just a moment, Jennifer, so you can see which problems we have. And here are the problems for 6-1. And so as you look at these, if you are on the computer, of course, they will not match up here, but it's 5, 7, 9, 11, and 13. Those are the odds between 5 and 13. Then 19 and 21, 25, 29, 31, 35, and then I skip down to 51, 57, 59, 63, 65, 69, 73, 77, and 79. And this is just basically Math 10, that first chapter section of that first lesson on decimal fractions, with the exclusion of whether one number is less than another. Okay? So with all that done, what about 5-7? The Q&A now on questions you may have done over the weekend that you'd like to talk about. 5-7 or 5-8? Okay, if we go to 5-8, so a lot of people were doing 5-7 is the reason I brought that up. But you have some from 5-8. Okay, let's go to 5-8 then. Which one would you like to look at, Isaac? Okay, it's a similar problem in the book. 45. Page 387. Okay, so we have some problems, or some pieces of wood coming together. It says 2 boards. Okay, so this is like a ruler with a ruler swiveling. And what do you know about these 2 angles that are created? What can you tell me? We've had a name for it before. Supplementary. The total is 180, correct? So these 2 angles have to be 180. And you're told that one of the angles is 1/3 of the other. So as I come to the board, and this again was number 45. So if I have number 45, section 5.8, and I have a diagram that looks a little bit like this. And one of these angles, if this is x, this one's 1/3 of x, correct? Now what must be true about the sum of those 2 angles? Must be 180. So it says that x plus 1/3 of x must be what? 180. You're missing 1. in front of the x. Yeah, that's the one you've got to remember. And then I like doing Natalie's distributive property. And I have 1 plus 1/3. And that's equal to 180. Now, what's the shortcut for going from 1 1/3 to a common fraction?
Put the 1 in as a 1? Yeah.
1 over 1 plus 1 over 3, or this is the mixed number 1 1/3, and don't you have a shortcut for doing that? 4 over 3. So we usually write the 4 over 3 in front, but now I have an equation with a what? With a fraction as a coefficient. So what do I do to get rid of the coefficient? Divide by 4/3 or multiply by its reciprocal. So Richie's reciprocal. Notice how each of you are starting to own a part of this course. Okay, so I'm going to take 3 over 4 times 4 over 3 times x, and equality now. What you do on one side you must do to the other side, to be fair. So that's 3 over 4 times 180. And what's nice, and Kim, this is just for you. And what do we have left?
1.
Thank you, 1. And so I have an x here. And now I would put this over 1 so I can cross cancel. Agreed?
You would do what now?
Cross cancel. 4 into here, 4 into there, and that's going to leave me 2 left over. So a 4, 5. James is correct. And now 3 times 45, 135, and I have it. Nice test question. Yeah, and it's until you deal with what this is telling you up here, the picture. Well, if I had 3 times 45 to get to that one, the other one better be 45, right? So 1/3 x is, of course, what I originally had before I multiplied by 3. So that is my 45. But again, let me come back first to what Isaac was talking about. Just to see that diagram, what had to be in your head before you could ever hope to get to this equation? That the total of those two angles is going to be the 180. And if that's not in your head, and you look at that diagram, you just see 2 boards. And it's like, okay, I've got 2 pieces of wood, so what? If you happen to note that these 2 angles are supplementary, that has to be information you just carry around with you. That those are supplementary, therefore this is true. Now, I make an assumption at this point that's dangerous. I say, gee, if you have this equation, you'll be able to do this and get from here down to here. Yeah. I'm hoping that's true. That makes me happy to know that I can assume that, and that you will then know how to solve for x and finish the problem. So the first difficulty is, how do I set it up? Once I get the equation, can I simplify it and solve? This is the point where most of the difficulties are. How do you set up the equation? How do you solve it once you get it? And that is what is the transition between pre-algebra and 70. Pre-algebra is, there are parts of it that are really straightforward. This is more of a just pure, unmitigated Math 70. No pre-algebra. It is 70, beginning algebra. Now, if you got caught on this one, you should be getting caught on some of these. Can you learn from it, and the next time you see one of these, say, yeah, I've got it now. So what things do we need to know about angles that allow this information to be at your fingertips? Supplementary angles. Complementary angles are what? It's the first letters before S. If this is 180 and C becomes before S, it's going to be a smaller number than 180. And what is it? Okay, before I get to your other question. 90-degree angle, 90-degree right triangle. So if this is angle X, and let's say, let me think for a moment how I want to do this. This is 2X. What do I know about X and 2X? With that diagram. Now you're thinking of Pythagoras.
Oh.
These are sides of the angles, not the sides of the triangle. They add together to give 90. Because the whole triangle must be what? 180. That angle there's 90. All three come out 180. So these two, since this is already 90 here, these two have to be complementary. So that's why I was saying complementary C before S. So X plus 2X in this problem has to come out 90, where in this problem it had to come out 180. So we said this is supplementary. And it's language, I know, it's more vocabulary. This is complementary. But that vocabulary is very important because it is exactly what you need to solve these problems. Now, I also commented that the sum of the angles in a triangle will come out 180. You're going to use that. And I have three different levels of problems I can do. I can do a problem where it's complementary, a problem where they're supplementary. I can do a problem where the angles for the triangle come out to 180. Okay? Any question? And again, a very good question about the kinds of problems in section, what is that? You said 5-8? Okay, Kim first.
I understand how to do this whole question. Except,
Okay.
how did you get the 180?
How did I get the 180?
How did you get the 180?
By knowing that these two angles making a straight line will total 180. That I had to know. Somebody had to tell me that.
Okay. Because that's not in the question.
I know, but that's part of what you're supposed to remember from an earlier explanation. So somewhere we had a problem where we said we had a straight angle. Yeah. You have to have it, something that tells you that in your head. Otherwise, you're toast. You won't get it.
Yeah, I didn't get
So this is part of that mathematical trivia. We need a mathematical trivia game. Yes, we do. Shammer's going, huh?
There's another one from the book, but I can't remember. I mean, from the
The computer?
yeah, it was on number 10. Trying to figure out the H. You got it?
You have number 10.
I thought that was wrong, too.
Okay. James, can you give me number? This is 10 on the computer, right?
Yeah.
So number 10 on the computer. 1 half plus 2n. Is that the one like what you're talking about?
Mine was
Half times H times, right?
with the
Triangle in the area?
Here's my number 10.
yeah, we're talking about the shape.
Is it 5-7 or is it in 5-8 then?
7.
Ah, because this is the 5-8 number 10, so we want a 5-7 number 10.
Which is this. It's that big word here. No, that's fine.
Is it the parallelogram?
Plus the two trapezoids.
Is this the one where we had,
The two trapezoids. Like 17 on top.
like, yes, this is, we did this one, 17 and 34? Yeah, we did this on Friday. Go look at the VHS tape. This is Friday's tape. Okay, so Friday's tape, we did this problem and a lot of discussion of it. Okay, so that's a nice way of finishing. Okay, you've got a problem. In the last minute I've got here. Not this one. So scratch this one. Okay. Parentheses. B plus 2. Close parentheses. Equals 9 over 4 minus B. Okay, I like that. Because this is 1/4 B This is Natalie's distributive property. 2 over 4 equals 9 over 4 minus 4b over 4.
How'd you get the 2 over 4?
I multiplied
All right,
Natalie's problem.
got it.
And now, notice the way I've done this, subtract 2/4 from both sides. This gives me 7/4 here. And add 4/4 to both sides. That gives me 5/4 here. And then multiply both sides by 4. That gives me 5b equals 7. B is equal to 7 over 5. And with that, I'm done because I've run out of time. Okay, so Jennifer.